Let me thank the ICMS for hosting this nice event where I get to see a lot of friends and colleagues. And also thank the organizer for giving me the opportunity to speak about work in PDE in my country. Okay. So when I was invited to give this talk, I took a look and I find it challenging because the PDE in Vietnam has been growing quite a lot since I left. So my starting point was Vietnam Mathematical Congress this summer that Professor Zhao mentioned in his talk earlier this morning. And there's one landmark. Is it is the first time that PDE appears in independent session in a meeting. And I do a simple count as 8 invited talks and 62 contributed talks. But if I look at the overall bigger agenda, I did sort of a not very careful count and already found 32 other talks in other sessions that could easily be fitted in PDE without any problem. So, okay. Then in terms of the places, so when I was a student there, most of the time when we talk about PDE, then one can think about the Hanoi University of Science or the University of Science in Ho Chi Minh City or the University of Education in both places. But now, if you look at it, then we actually have quite an impressive list of universities that have active PDE researcher. So this list is by no means exhaustive. Basically, I'm just doing a Google search, and then I just try to find as many as I could. And at some point, I think I got to stop because there's no end in this game. Okay. Then let me go on to the kind of topics that that I have seen. So I was trained in inverse problems, so that's where I looked at in the first place. And so Dang Đức Trong is my undergraduate advisor, and Professor Dinh Nho Hao. And you see a lot of name here, so I will not talk. The name here just some examples, so I will probably likely miss a lot of names, and that's not intentional, but it's just simply not possible to mention everyone. So instead, I will focus on the math. I think this pointer is not working. Okay. So in inverse problem, there are a few topics that has been very popular for inverse scattering or inverse heat conduction, and about U-pose problem and regularization procedure. So later in the talk, I will give you an example of this where, for example, let's take the problem of the inverse heat problem, where instead of, so the forward heat problem is that we prescribe the heat distribution at the initial time and we solve it forward. Now, if we do the opposite, say, suppose I know what happened today, can I find out what happened yesterday, and so on. So this is a new problem, and but it has practical importance. So then one need to come up with way of regularizing it or way of approximating the solution in a way that is stable. Then there's the area of nonlinear elliptic problem, where there are a lot more younger people actively working on it. And I list here a few topics that have been dealt with in the last 10 years that I see and got quite well known in the community. So such as the theorem of a Liouville theorem in this context, or the study of the infinity Laplacian, the Hardy-Henon equation. I don't know if Ngô Quốc Anh will talk about it on Thursday or not, but okay, let me just mention it. And the Hessian equation. Then parabolic equation, you can also see quite a lot of research here. So the study of stability, it has been rather strong. And one thing that I find quite remarkable is that the issue with delay that come up in these studies. So delay is something that is not very popular somehow, because it's a lot more challenging, but somehow we seem to be very interested in this. And in terms of practical importance, it's very important, but in terms of mathematics, in a way that instead of dealing with finite dimensional vector space, then all of a sudden you just put it up to infinite dimensional space. If in a very naive way of comparing a system or equation with or without a line. Hyperbolic equation has also been a lot of progress. So I will probably go back to these things later on. So so then there's a few things that I will not talk about later in the talk, but there are several complex variables which I know very little about, and so I only put down the name here and the kind of topic that, but I'm afraid I would not know enough to have any discussion on this. There's mathematical biology, the Navier-Stokes equation, and there are furthermore, functional inequality in space. It's not exactly PDE, but you could use it. You can use PDE techniques in it, or this could be useful in studying PDE. There's also a group doing Schrodinger equation. And there is a growing community in non-low equation. So this is very similar to what happened in the West, where we see more and more paper in non-low equations. Sometimes I have a chat with some of my colleagues who are doing non-local equation. I keep asking them, what is the focal point for non-local equation? And I don't think I get the answer. It says basically we can do things for local equation. Let's try to do it for non-local equation. I think it's good, but I think at some point one need to refocus and find out what it is that we need to do here. And there's also a growing, perhaps growing rapidly, group of numerical analysts, and I'm not a numerical analyst, so I would not talk about that at all. Okay, so then I read around 60 papers, and I chose 3 to present. Okay, so here is a problem that was studied by some group of Vietnamese mathematicians. So let me just start with the history of it. So around 2005, Savin make a breakthrough in the understanding of the infinite Laplacian. So the operator is just the sum of right. So you take the Hessian of U and then you just contract it with the gradient of U. Then the result of Savin is that if you look at the infinite Laplacian of U is equal to a function, then he say that the solution is on the plane. The solution is C1, and 3 years later it was improved to C1 alpha in a work with Evans, and a few years later Evans and Smart proved that in high dimension the solution is almost everywhere differentiable, and this is the best known result so far in high dimension. So now in part of I don't think I know how this works. Okay, so part of Savin's work, as an application of his work, he deduced that if a function U is infinitely harmonic on the whole plane, and if it grows at most linearly, then the solution is constant. So this sort of resemble the theory of standard harmonic function, right? So where in the other case, the conclusion is that U is an affine function. In this case, U is constant. So this has been extended by other people. So in around 2016, there's this result where the right-hand side is not 0 anymore. It's the right-hand side is a lambda multiplied by the positive part of U raised to the power beta, and with a technical condition that beta has to be less than 3 and positive. And suppose that U is now, instead of being sublinear, now it's subpolynomial with a certain growth here. Then U has to be constant. Yeah. So what we see is that, okay, now there is some generalization by Biswas and Võ Hồng Hưng. So suppose now we look at more general Pareto, where so this sum here is just the infinity Laplacian, and you just modify it by 1 over the norm of greater u to the gamma, and then we obtain, they obtain those kind of Liouville theorem, right? So suppose that now instead of an equation, now they talk about inequality, and now it's on any dimension now. Or they can look at the case where there is an advection term. Okay, so so the method that they do in these work are very different from Sabin. So that's one remarkable thing. And so if you look at the proof, it's very nice. I will not go very technical in the proof. I would only mention that there's 2 ingredients in their proof. So one is a suitable barrier, and this one here you can give it to an undergraduate student. You tell them the equation, you tell them to look for barrier, they will cook up for you. If you give them a cue that just look for a solution in radial symmetry, they will be able to find it. So the main thing here is the comparison principle. Okay? So why is it that it's difficult? So the problem is actually degenerate elliptic, and one knows very well that the strong comparison principle or the Hopf lemma might not work well with the degenerate ellipticity. So here I give a very simple example. So let's consider the motion pair equation, so determinant of a Hessian. Right, so this is right. So now I take u to be the function 1 plus kx1 squared, where k is positive, and v is the function, the constant function 1. Okay. So now both u and v are convex, and the role of the number 1 here is not very important. You could take it to be 0, but I put it 1 because sometime in PDE, when you look at positive solution, it might help. So I put the 1 there just to make it positive, to highlight the point of positivity is not playing any role. Okay, so in this case here, the determinant and Hessian are both 0, so they're equal, right? And we have a situation where u is bigger or equal to v, right? So u is actually a convex function like this. V is a constant function. They touch along a plane. However, they're not identically the same, right? So for uniform elliptic equation, we know that situation never happens. When you have a solution and another solution, and they touch at an interior point, they have to coincide everywhere. Yeah. So in a uniform elliptic equation, that's okay. But in this case here, where one has degenerate elliptic, those strong maximum principle doesn't hold. So it's quite remarkable that they managed to do it in that particular context. So a lot of time in this case here, they have to do case by case analysis. Okay, so that's one example. Another example has to do with semi-linear wave equation with a damping term. So first you look at so u here is a vector value map. So it goes from 0t cross Rn into some Rk, say. And so here I have the first term here, just the D'Alembert, we all know. And the dtu here plays the role of damping. And on the right-hand side, there's this nonlinearity of power type. Okay. So the boundary condition here, I put rho in here, but for simplicity, you just take u equal to 0 on the boundary if you want. The point here is that I look at only small data, initial data. So let me explain a bit of history of this line of work. So for this case of scalar equation, it's well known that there is this exponent p called a Fujita exponent. So such that if p is bigger than this Fujita exponent, then you have global existence regardless of the size of the initial data. On the other hand, if p is less than or equal to the Fujita exponent, then you have only finite time existence. So the solution will blow up in finite time. And it has been shown that the existence time is proportional to a negative power of epsilon if p is subcritical, and it would be exponential of a negative power of epsilon if p is critical. So these are all sharp. So in terms of both upper and lower bound. Okay. So this rings a bell to a lot of work by Strauss and Fritz Jones in the 70s, Jones in 80s, Sappho, so 90s, Lassie, Sideris, Lindblad, and Sork in the 90s, and what we have seen now is that so now all of those work has been extended to a system where there are two or more equations. So the kind of thing that they are interested in, so in particular here, I mentioned here the name of Dao Tuan. So they the kind of criteria they want is that it's a function, right? So it's a function of the exponent P1 and P2. Right? If it is less than n/2, then they actually have finite time blow up. And if it is bigger than n/2, they have global existence. And the same work has been done for existent time. And even more remarkably, just this year, they managed to do this for larger systems. So this is now true for any arbitrary system. So it's if you look at the proof, the starting of the proof are very similar to what happened for scalar equation. It's a fixed point method, but then in order to get upper and lower bound for solution, you need to come up with very specific method to catch it, and it requires a lot of technical power to handle all of that. Yeah. Okay, then I think I'm doing okay with that. So the last one I will talk about is just the backward heat equation, so which I mentioned earlier on. So suppose I have the heat equation, it looks like the heat equation, and F is he is a function of T and U, and I suppose for simplicity it's a Lipschitz function on R cross O2 omega. And I put the zero boundary condition, and I put a terminal on data. Right? So I don't put U of 0x, but I put U1 of x is the given data. Right? So the terminal. So this one here, you can show that it has uniqueness, but if you change the terminal data phi a little bit, the solution might be disturbed heavily. So according to Tikhonov, he called it severely ill-posed. Because mathematically, we know what is a well-posed problem and an ill-posed problem, but he called this problem is severely ill-posed from his point. Okay. So this has been studied by a lot of people since the 60s. So start with the work of Lattezel and Tikhonov and Asinin in 70, and Showalter in 83. And afterwards, there's a large body of work by a lot of Vietnamese mathematicians. Okay, so I think Nam is not here yet, but he contributed to this kind of work as well. So here I only show you what they did. Okay, so suppose that you have you look at the Laplacian operator and you call the eigenvalue lambda 1, lambda 2, lambda 3, and so on, and the eigenfunction phi1, phi2. Right, so then every L2 function will have an expansion as an infinite sum of ck, phi k, and then they define this operator a beta in this way. So the reason why they come to this expression is perhaps too technical to explain in the talk. But anyway, so once they define it something like this, then one can see that a beta formally go to delta minus delta as Laplacian is going to 0. Right? So when beta is going to 0, this whole term here becomes simply just lambda k. And so you have a sum of lambda k, ck, phi k. So that's just the Laplacian acting on this infinite sum. Okay, so what they do is the following. So suppose that you approximate the initial data. Let me try it again. Okay, so you approximate the initial data phi by phi beta. Then instead of solving the heat equation, right? So we know that if we try to solve the heat equation directly, then the solution might not converge back to your solution. So what they do is that they replace the Laplacian operator by that operator a beta, and they solve it. Then they manage to show that, first of all, this equation here will have a unique solution. That's not very hard to show. The important part is the later part, right? So not only that it has a unique solution, but as you send beta back to 0, you get the conversion of your solution to the exact solution, right? So from a practical point of view, this is important, because suppose you do a measurement, then you measure the terminal time, the terminal data, that might not be exact. Right? If you solve the inverse heat problem, the backward heat problem, right, the disturbance between what you calculated, the exact solution is very big. But now what they propose that instead of solving the backward heat equation, you solve this kind of functional equation instead, then it actually approximates your exact solution in a much better way. But it carry the caveat of that is that this condition on the solution. So it turned into some of the condition, but if you pay attention, this weight here is exponential. That's very bad. So that means that it requires a lot of regularity. So you have to suppose that your solution is a lot more regular than what you have. Okay, so that's the kind of thing that we see. Yeah. Okay, so I think I'm ahead of time, but let me just summarize and I will stop here. So from my point of view, PDE research in Vietnam is growing rapidly, at least since the time that I left. Much effort is placed on topic with an established history, and some of the history can go back to the 60s or 70s. Okay. Now, what I see as a shortest is that there's a very limited output on things that are more pressing in modern topics, such as PDE that has multi-scale nature, or PDE in nanotechnology, PDE in complex fluids, in image processing, data science, for example. I don't see a lot of those. I see some, but not a whole lot of those. So, and the last thing that you probably see from the list, that the number of female research are very small, very, very small. So, okay, so with that, I will stop my talk.
We have time for a couple of questions. I have a question on the mass theorem.
Yeah.
It's very interesting to me.